So with this, I'd like to talk a little bit about how we do numerical computing in Python. And one of the reasons I'd like to talk about this is that this is a strong reason of why Python became so popular in data science the last few years. And I was doing numerical computing in Python before I started doing data science. And I came to this field with a good knowledge of numerical computing. And I think that's very important if you want to do data science to a very advanced level. So the core of numerical computing in Python is a library called Numpy. And let me show you a bit why people in numerical computing love it. So suppose we want to capture the term frequency versus the inverse document frequency across many, many documents, okay? So for this, we're going to need to, well, here I multiplied. We're going to need to multiply the two numbers, okay? Suppose I've stored the inverse document frequency in a list that I call IDF, and I've stored the term frequency in another list that I call T. So I need to take every element of those two for every term, and I need to multiply the two. So I can write this in Python with list comprehension. This is a very tight syntax. I love it. And it's going to take, in this example, it took 6 milliseconds. Now in Numpy, the way I will do it is I'll just write the expression on the arrays. In Numpy, these are no longer lists, they're arrays, so they're tables. And I'm writing the expression. And this is significantly faster, much, much, much faster. And you can see that as I vary the size of the list or of the array, the Numpy it keeps being much, much faster. Okay, so why is it faster? Well, let me give a bit more detail of how it works. Another bias that I personally have is that because I'm trained, I find that this syntax is much more readable than this syntax. This is a bit of training, because this is an array computing syntax, which is common to R, MATLAB, many array languages, and this is like a general Python syntax. So once you're trained, you might like this. Okay, so in practice, arrays are nothing more than pointers. So if you do see, so what a NumPy array is, it's a memory address, so a pointer, a data type, and then a shape and a stride. And shape and strides are numbers that tell you how you're going to move across the memory when you're trying to address the different elements of the array, okay? It tells me that if I want to go from one number to the next one, I need to jump in the memory by a certain stride. And then I can jump, 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 jump. And then if I jumped enough, then I need to loop back. And to loop back, I need to jump by the second stride. And in NumPy, this is multidimensional, so I can have as many shapes and stride as I want. You don't need to know this to use NumPy, but this is the underlying model. Okay, this model is powerful because it can represent any regular data in a structured way. So any regular data, I can represent it in an efficient way. So basically, it's like a higher level abstraction of pointers and data types. In practice, in memory, this is just something that is continuous. Why is this important? Because this matches the memory model of just about every numerical library. So the numerical libraries that have been built for years and years and years in scientific computing can be used without copying the data because we're just giving them the pointer. And this is one reason why we're efficient. So in my opinion, NumPy is really a memory model. Okay, so memory computing is extremely fast because we don't need to do time checking when we do this, but also because it creates a direct sequential memory access, right? So in terms of memory access, we're accessing the memory in a continuous way, and that's extremely efficient for the hardware that does the memory access, and that's extremely important. And the other thing is that it can be computing using vector operations, okay? Now, have you noticed that on the graph I was showing, there was something that was happening at a certain point? This is the time per element as a function of the number of elements in the array. And at some point, it starts going up. Do you know why? Memory, yeah, pretty much cache. I mean, memory, if we had even more data, it would be memory. We would start accessing the disk. So the reason is when our arrays are too big, they no longer fit in cache. When they no longer fit in cache, the CPU needs to move data in and out the cache. Now, the important thing in modern memory computing, thank you, is that the memory is much slower than the CPU. So what you want to avoid is to avoid moving data in and out the cache. So well, okay, I'll walk you through this. So it gets even worse when I'm trying to do real computation. So here I'm trying to do TF-IDF minus one, which is something that is often done. So then I mean, it gets really worse. Bang, it starts increasing a huge amount. So why is this? What's going on here is that first there's an array that's computed that does TF-IDF, and then there's another array that's computed that does TF-IDF minus one, okay? And each time we're moving data in and out the cache. So this is extremely inefficient. And so we can improve, so you can see this. I mean, the cost here has been huge because we've just moved data hugely out of the cache. So the challenge is going to be to write the code to minimize this. And one way is to use in-place operation. Here I'm using a minus equal. The minus equal uses an in-place operation. And because the operation is in place, it knows that the data that comes in is the same as the data that comes out. So it has twice less data to move, okay? So if we're moving twice less data, the cost is twice as small. As simple as that. So if you want to optimize numerical code, you're going to be doing basically in-place operations, okay? So this can be seen as a compilation problem, and there's a bunch of modern libraries that try to address it as a compilation problem. Thing like numx or numba or lazy array, and this is related to pagination with SQL queries if you're good at SQL. So what I'm saying is that another kind of abstraction can address this, but it's just not universally deployed currently. All right? So the take-home message is that when you're doing array computing, you can either have tiny arrays and then you're limited by the overhead, or huge arrays and you're falling off the cache and you're limited also. I'm going to skip this in the interest of time. The only thing I want to say is that when you have mixed data types and say you have columns of strings and columns of numbers, then it's extremely useful to use a library that's called pandas, and that is basically a blend between the Numpy model and a database model. So it can do things like queries and equals in a very good way, but it's less good for numerics. So I will strongly push people to use pandas when they have mixed data type and to not use pandas but Numpy when they don't have mixed data type. So often what we do is we start with pandas, we bunch the data, at some point we fall to numerical values, and we go to a Numpy. Okay? So really what we're doing is we're converting the data as a number, and then we're just importing scikit-learn, and it's easy.